All right. So in this talk, I'm going to tell you about our new library for verifying distributed systems using separation logic. Distributed systems have to deal with a lot of corner cases and subtle behaviors, stemming from the wide range of issues they handle, including many of the aspects listed on the slide. A promising approach to building these systems correctly is formal verification. Formal proofs can ensure that a system is correct across all the corner cases and subtle behaviors. Prior verification work has even shown how to handle many of these aspects of distributed systems individually in isolation. However, real systems often make use of all these different aspects and in ways that interact with one another. In this work, we set out to reason about these systems by verifying all their aspects as well as the interactions between them. And to make this more concrete, let's look at a linearizable key-value store that we built as an example. So this linearizable key-value store is replicated. So there's replica servers that each have a full copy of the key-value state, and when a client wants to do a put, it gets sent to all the replica servers. The system also implements reconfiguration, allowing switching to a brand new set of replica servers as long as one of the old ones is reachable and by making use of an external configuration service. A key consideration we have to make sure that reconfiguration is implemented correctly is we have to make sure that there's no lost put operations. And this is subtle because replication in the old configuration might be trying to add a new put operation while reconfiguration is trying to set up a new set of servers. Another aspect of the system is a performance optimization that allows handling read operations from a single replica server using leases. Leases are a distributed system technique that allows for using clocks to avoid coordination and to make sure that some piece of state is up to date. And a key consideration we have to make in this lease-based optimization is that when a replica server handles a read request on its own, it must be the case that there's no new configuration that is started, since the new configuration might have more operations this replica doesn't know about. And we can sort of start to see this picture is starting to get a little bit complicated because of all these different aspects and all the arrows interaction between everything. So to sort of distill what we're really trying to do, the goal is to try to prove the following top-level theorem, which says that put and get are linearizable in the presence of all the other aspects of the system, including reconfiguration, concurrency, and so on. In this work, we introduce Grove, which is a proof library that helps you state and prove theorems just like that. The core of Grove, the sort of approach of Grove, is a proof technique called concurrent separation logic, which I'll shortly talk a lot more about. And on top of CSL, we support reasoning about all these different aspects of distributed systems that I mentioned, as well as the interactions between them. In addition to Grove itself, which is a library for verifying distributed systems written in Go, another contribution of our work is a few brand new reasoning principles for distributed systems, such as for leases and for RPCs, which might even be useful for others building other verification approaches. And finally, we built a case study of distributed system components shown in the graph on the right, and verified them all using Grove. And in this talk, I'll only have time to talk about a small slice of these components, and I encourage you to look at the paper for all the other details. So let's start digging into how Grove actually works by talking about its sort of high-level approach, which is concurrent separation logic. Concurrent separation logic is an existing and successful proof approach that's been used in a lot of recent and prior work. Here in this work, we extend CSL to work with distributed systems. And to sort of preview the sort of theme of the talk and sort of the punchline, what we get out of doing this is the ability to verify different components of a distributed system separately while still verifying the interactions between them. And these two things sound like they're at odds with each other, since how can you verify components separately and also make sure you handle the interactions? And the key to understanding what this means and how it works is the idea of ownership in concurrent separation logic. So the idea behind ownership is that the assertions that we use to reason about code that we use in proofs don't just talk about what's true, but also denote ownership or some sort of exclusive permission to access some resources. So the way we'll reason about a simple piece of code like this is we'll think about the resources that it owns as it executes. The relevant resource for this piece of code is a heap resource, x points to v, which represents the fact that address x currently has value v on the heap and denotes ownership of address x. And what ownership really means is that no other threads can simultaneously own this address x, and as a result, can't access or modify x at all. And that allows us to verify our piece of code all on its own without worrying about what these other threads might be doing. And to clarify, these resources are a proof construct to help reason about the code and don't actually show up in the running execution. Another important concept from concurrent separation logic that we build on is the idea of invariance, which allow for sharing resources across multiple threads. And to illustrate this, here's an example in which two threads access a shared variable y using a lock to synchronize access. The way we reason about it is by using a lock invariant, which maintains ownership of the resource y points to w for some arbitrary value w. This lock invariant can be accessed by the threads when they call lock. So for example, when thread 1 calls lock, it'll gain ownership of the resources that were previously inside the lock invariant and be able to use them for its proof. And when it calls unlock, it returns the resources back to the invariant so that future lock holders can make use of them. And what this allows for is we can verify different threads of the program independently of one another. So the way we verify thread 2 is the exact same argument, and we don't have to consider when verifying thread 2 what exactly thread 1 is doing. The last important concept that we build on from concurrent separation logic is the idea of generalized, sort of more general resources. And the idea is that with more general resources is that ownership doesn't have to be all or nothing, that you either own something or you don't, but can allow for sort of different views on one piece of state. And to illustrate this, let's look in a bit more detail how the key value system keeps track of configuration changes. The system uses monotonically increasing epoch numbers to keep track of what the latest configuration is and what configuration each server is in. So the config service itself keeps track of the latest epoch number that the whole system is in, and each replica keeps track of which number they in particular are in, which might be an old number if it's an old replica server. The way we model this state in the proof is with two ghost resources. The first of these, the current epoch points to E, represents ownership of a monotonic epoch number and is owned by the configuration service, which represents the fact that the configuration service knows exactly what epoch number the overall system is currently in. The second resource, the current epoch greater than or equal to E, represents knowledge that the epoch number has at least reached E. And this resource is owned by all of the other replica servers and represents the fact that whatever epoch these replicas are in was once the latest epoch of the system. And what this allows for, what this kind of ownership allows for, is reasoning about the resources that the one server owns independently of the others. So for example, the config service owns the current epoch points to E and can freely change its own, increment this epoch number and change its ownership of current epoch points to E plus 1 without worrying about invalidating the lower bound resources of any of the other servers. And now that we've seen some of the pieces of concurrent separation logic that we build on, let's see how we actually use them to verify a particular interaction in the linearizable key value service. And the thing we're going to focus on is the least-based optimization and how it interacts with reconfiguration. And to remind you, the key consideration in this is that we have to prove that when a replica server handles a GET, that there's no new configuration that's started. And the way the system actually implements this and achieves this is by using time-based leases. A time-based lease is a promise that some aspect of system state won't change for some amount of time. So for example, a key value service might say that a particular key has a particular value for some amount of time. To have a consistent view of which leases are valid or invalid, we build on clocks that are synchronized within some known error bound, with an API very similar to Spanner's true time. The particular lease in the key value store is a lease given out by the configuration service to replica servers, promising that no reconfigurations will happen for some amount of time. This happens in a background thread with periodic notifications to replica servers. When a replica later receives a GET operation from a client, it first checks to see at that moment if the lease is valid. And if it is, it'll read its state, it'll read the key value pair from its local state and eventually respond to the client. And to sort of make sure that this plan is correct, we have to prove that when this lease check succeeds, there must be no new configurations that have started, or in other words, no new epoch numbers that have been created. Meanwhile, other parts of the system might be trying to run reconfiguration, and a key step of reconfiguring to a new set of servers is creating a new epoch number, which is handled by the configuration service through this enter new epoch RPC. And what this does is it first waits to make sure that all the leases that it's given out have expired, and then increments the epoch number and returns to its caller. And to make sure that this part of the system is correct, we have to prove that when the config service increments the epoch number, that there are no leases, there's no servers that still think they have a lease out on the old system, and they will no longer try handling any more gets. The way Grove supports reasoning about leases is a new idea called time-bounded invariance. And the idea behind time-bounded invariance is that we formalize the notion of a lease with shared ownership that's only valid for some amount of time. So the dashed box containing some resources represents the time-bounded invariant itself. And the label L is a sort of is an identifier that keeps track of which particular time-bounded invariant we're talking about. And it allows us to use separate resources that keep track of and talk about the expiration of this particular lease or time-bounded invariant. And to better illustrate how these different resources get used, let's see how we use them to reason about the key value store. So the key ingredient is a time-bounded invariant that maintains ownership of the current of a current epoch points to at a particular value E, which is the epoch that the replica server is in. In this picture, the solid line represents the duration for which the time-bounded invariant is valid, after which it may no longer hold, since this ownership is only temporary. And let's focus first on how the replica server makes use of this. The replica server keeps track of a lower bound resource L greater than or equal to T, which represents knowledge that the lease is at least valid until time T. It gets this from periodic notifications from the config service in a background thread. When the replica server receives a get operation, it checks to see if the lease is valid, which more specifically means checking to see if the current time is less than T. Assuming it is, it can combine its ownership of L greater than or equal to T together with the fact that the current time is before T to use an access rule for time-bounded invariants and gain ownership of the current epoch points to E. This ownership is only temporary since other replica servers might also be relying on this time-bounded invariant, but it's still enough to make progress in the proof. And in particular, we can rule out possibilities that are inconsistent with this ownership. So we can prove that by virtue of temporarily having this ownership, that there are no new epoch numbers that could have been created. We then return the ownership back to the time-bounded invariant and can proceed along with the rest of the proof, being certain that the state that we're reading is not stale. And what's sort of notable about this proof argument is that this proof didn't at all talk about what exactly the config service is doing. And to sort of fully understand how this is still capturing the interaction between the two of them, let's look to see how we reason about the config service and sort of forget about the replica server for the moment. The config service is the grantor of the lease and so maintains ownership of L points to T, which represents, which is ownership of the exact lease expiration time. When the config service receives an enter new epoch RPC, it waits and in particular waits until the current time is bigger than this exact lease expiration time T. And at that point, it can combine its ownership, its exact ownership of the lease expiration time, together with the fact that the current time is beyond that, to use an expiration rule for time-bounded invariants, which allows it to get permanent ownership of the resources from inside of it. This ownership is permanent and doesn't need to be put back because from here on out, the invariant is anyways invalid and nobody's going to try using it. This allows the config service to increment the epoch number, including this current epoch resource, and reply to the client, including a witness, this lower bound witness, that the epoch number has actually been increased. And in the future, if future replica servers want leases, the config servers can use even more rules related to time-bounded invariants to create a brand new time-bounded invariant for the new epoch. And the sort of key takeaway from looking at this example is that using ownership, and in this particular case, a time-bounded invariant, it's possible to verify these different components of a distributed system separately. And so our overall case study includes this linearizable key value store and leases and reconfiguration, but also a lot of other stuff, including crash recovery and durability, a Paxos library, a lock service, and some basic distributed transactions at a top-level application. All this stuff is implemented in Go and adds up to around 2.4 thousand lines of verified code. Each of these components were verified and spec'd out separately, adding up to overall 28,000 lines of spec and proof. And a sort of key takeaway from this is that the proof to code ratio is around 11.5 lines of proof for one line of code. And this is a very rough measure, and this is sort of a high number, but is actually pretty in line with prior verification work and shows that handling all the interactions and all these different aspects of a distributed system doesn't come at an inflated cost in terms of the proof effort. In addition to verifying the case study, we also evaluated the performance. And one question we asked is whether leases and the way they interact with everything else is actually an important part of the system's performance. And in this experiment, we run an instance of the key value store and two sets of clients, one which continuously does get operations and the other doing put operations. Initially, we run the key value store with two servers, a primary and a backup. At some point into the experiment, we kill the initial primary and start reconfiguration and switch over to two brand new servers. And while this is happening, the clients keep track of their instantaneous throughput that they're measuring, averaged over half-second time slices. This graph shows the read and the write throughput as this experiment is running. So worth noting at the beginning is that the read performance is much higher than the write performance. And this is because reads can be handled by either replica server individually without having to talk to the other one, whereas writes have to go through both of them. At around 20 seconds into the experiment, we kill the old primary and start reconfiguration. And what's notable here is that even during reconfiguration, the one remaining backup server has a lease that's valid for the vast majority of reconfiguration and can still handle a lot of read operations. Eventually, once reconfiguration is done and the new configuration starts, the performance of reads and writes picks back up to their earlier levels and the system can continue running along. This is all the performance evaluation I have time to talk about right now, but I encourage you to look at the paper for more details about that. To summarize, in our work and in this talk, we sort of show we show that it's possible to verify distributed systems that have a wide range of aspects, including all these things that I've listed here, and their interactions. The way we do this is by using concurrent separation logic, or CSL, and some new ideas like time-bounded invariance. And finally, Grove itself is open source, so we hope that people in this audience will poke around at it and even try building on it in future work. Thank you.
Hi, Brad Karp from UCL. Thank you very much for the talk. I wanted to ask how we can think about the frontier of what these CSL techniques can cope with in a distributed system and what challenges remain. So, for example, for a distributed system with more complicated semantics than a linearizable key value store, or for a distributed system that even just supported, say, leases with revocation or something like that. Can you describe what the next steps are, or what more needs to be done still?
Yeah, so let me, I guess the two sort of specific things you listed, let me go one by one. I think it's an interesting and sort of somewhat open question how to effectively specify systems that have weaker consistency, particularly in a logic like concurrent separation logic. I think there have been some works that have tried to specify things like causal consistency, and the specs are quite complicated and a little hard to read and make sure you got right. And I think things, things even weaker than that, like eventual consistency, are even less clear how you would specify them in CSL, because it's talking about something that will eventually happen. So I think there's a lot of, I think there's sort of open questions in terms of how to specify these other kinds of systems. And in terms of extending support for other sort of, other ways of, for example, using leases, such as if we wanted to revoke leases, I think the sort of approach for going about that would be to take this sort of time-bounded invariant library that we have and try extending it by sort of changing the sort of implementation of this library, changing the definition of this time-bounded invariant, and trying to prove some new lemmas about under which cases it's possible to actually reclaim the resources even before the lease is expired. So I think it's concurrent separation logic is sort of just a language for being able to express a lot of sort of these kind of patterns, and it seems promising and totally possible to talk about things like revoking leases.
Okay. Thank you.
Yeah.
Next question.
Hi, Steve Hand, Google. Great work. I've got a kind of a conceptual meta question, which hopefully we can get to. I noticed in your paper you did some performance comparisons with Redis.
Yeah.
And you weren't quite as fast in some cases, but it's obviously not a like-with-like comparison, right? There's different programming languages, different bits and pieces.
Yep.
So my question is, do you think are we going to find that there are inherent performance trade-offs versus correctness trade-offs that exist in the way we think about these distributed systems? Or should we be able to have verified and highly performant things? What's your kind of hope?
Yeah, so I guess in principle, I think I see no reason why it shouldn't be possible to verify a high-performance system. So for example, in principle, you can imagine verifying Redis, and in practice, it's just a lot of work. So you saw it was like 11.5 lines of proof for one line of code. And so I think verifying system, even more realistic systems, or off-the-shelf production systems, is sort of has open question and sort of future work. And I think it's totally possible by sort of making these techniques easier to use and more automated and stuff like that.
Thanks.
Yeah.
Next.
Hi, it's Matezebe from UC Berkeley. Thank you for your talk. I had just a small question to be sure I understood correctly what you said. So on your 20th slide, you said basically that the configuration service will wait for the exact moment at which the expiration of lease happen, of the ownership, sorry, before taking the full ownership. And yeah, and I just want to make sure: is it not possible for another operation to happen just at the end of the expiration, before the configuration services take the ownership?
So you're talking about a get operation that starts right as...
Yeah, just before.
Yep. So the way that gets handled is when a replica server handles a get, it first gets a lock on the state, checks to see under this lock whether the lease is valid, and then actually reads the key value pair in response to the client. And so this whole thing by virtue of the lock is sort of atomic. And so what actually matters is that some point in time during this critical section, the lease was valid and that there were no new configurations. If by the end of it a new configuration started, that's still okay because the get operation is linearized at the moment that the lease was valid. Does that help?
Yeah, definitely. Thank you.